Okay, so let's talk about the basics of probability and Bayes' rule. Okay, so you don't really need to understand like what's going on here in the sense that if you want to skip the background, like the handout tells you like what numbers to code up, but I think it's useful to have some um, sense for why we're doing what we're doing. So the basic idea in probability, so you might see this if you take maybe Math 132, I think it is, elementary statistics, or Math 231, 232, probability and statistics. I forget exactly the course numbers, but things like that. You should definitely look into those because probability and statistics are one of the most important topics in math for machine learning these days. So if you're thinking about going into the tech industry, then it's really important stuff to know. So what we'll write notationally is like a capital P for probability. And we'll write things like, P of sunny or P of raining. So sunny and raining are what are called events, which are things that might happen. And P of sunny is like, write that phrase as the probability that it's sunny, and P of raining is the probability that it's raining. And so these are going to be numbers in the range 0 to 1, which you think of as like the chances of something happening. So, if P of sunny is 0.25 and P of raining is 0.35, maybe there's a P of cloudy as another possibility, which would be the other 25, 40%, and so on. So that says like there's a 25% chance it's raining, it's sunny, 35% chance it's raining, and a 40% chance that it's not sunny and not raining. It's just cloudy. Okay, so we'll need that notation. Um, the other notation that we'll need is, so like in general, I'll write P of A for the probability of an event A. We'll also need the notation of P A bar B, which is called the conditional probability, which is how likely is A if B happens. So rather than thinking about how likely is it um, that it's raining, right? So like we could say, for example, what's the probability that it's raining given that it's cloudy? Or what's the probability of it raining given that it's sunny, right? So it's the idea of like, what's the chances of this event happening that it rains given that the sky looks like cloudy or sunny? And you can imagine that those might be different, right? Like the probability that it's raining given it's cloudy might be bigger than the probability that it's raining um, overall, whereas the probability that it's raining given that it's sunny might be less than the probability that it's raining overall, though you would get a nice rainbow out of that. And okay, so that we need the idea of the probability of an event and the conditional probability. And so then with those in mind, the idea of Bayes' rule is that it says that the probability of A given B is equal to the probability of A outright multiplied with the probability of B given A all over the probability of B. Okay, so I'll do the abstract form first, but in a second we'll do an example to try and understand what's going on here. But the reason that this is going to turn out to be useful for making us doing machine learning is that it lets you flip. I want to know what are the chances of A if I observe B into what are the chances of A outright, what are the chances of B outright, and what are the chances of B given A. So it lets you turn A given B into B given A, which turns out to be a useful flip because for whatever reason, these quantities here are going to turn out to be easier to observe in the training data. So in the data that we're learning from, it's going to turn out to be easier to learn these things. And so we're going to observe these quantities from the training data and then use those to make predictions. Okay, so let's do an example. So kind of the standard example that you run into of Bayes' theorem is particularly appropriate these days. So suppose that you want to know what's the probability that you had coronavirus given that you have a positive antibody test. Okay, so I'll write, sometimes I might write C for that and A for that. Okay, so imagine that, we get our blood serum antibody testing for did you have the virus up and running? Then the question that you're going to be interested in if you get a test is what's the likelihood that I already had coronavirus so I can, go out and do my grocery shopping without being worried about getting a virus, given that my test came back positive, right? So if you get back a positive test. And so the idea, right, so this is like, if you get back a positive test, this is your mental model for how likely am I to be safe now, in the sense that like I should hopefully have some immunity because I already had coronavirus. And so if we rewrite this using Bayes' rule, it says, what's the probability that you had corona already divided by what's the probability of a positive antibody test times what's the probability of a positive test assuming that you had coronavirus. Okay, so it's letting us flip the probability that you had the virus given a positive test into the probability of a positive test given that you had the virus. Okay, so why is this useful? Well, we might be able to find out the probability of corona outright by some kind of community survey. So for example, suppose we do a randomized study of a bunch of the population, we might discover that like in your area, 5% or 20% or whatever of the population have had coronavirus already. And so this is what's called a prior, sometimes, in Bayesian probability. And the idea is that that's sort of like what you would guess even without knowing anything about your positive test. And so if we did a good uh, randomized, everybody gets a swab in the mail and mails it back or whatever kind of mechanism to just test and find out how many people had the virus outright, then once you know that, the idea is that your baseline base rate of idea of how what you should think is that, well, there's a 5% chance or a 20% chance that I was one of those people. And so then the question is, how much does having a positive antibody test um, update your belief in and make you think that like you're more likely to have had it? And so the probability of a positive test, given that you had corona, is what's called, I think, I always get these terms backwards, but sensitivity of a test. And that's something that like the drug companies will try to measure. But, okay, right. So like how do we get an estimate of this? Well, you administer the test to people who you're pretty sure for other reasons had the virus. So, for example, if we're talking about an antibody test, then you could administer the antibody test to people who previously tested positive via swab for the active thing when they were sick and had symptoms, or maybe didn't have symptoms because we want to include the asymptomatic people, right? So, like, there's a question of getting a good estimate of this, but if all you're interested in is the probability of positive test for people who had the virus, then you could just use some other test and only test those people. Um, and so then you don't need to take the like asymptomatic people into account for this one, because in this one, you're just interested in what's the probability of a positive test, assuming that somebody already had the virus. And so it's enough to just test the people who you're pretty sure had it via some other test. And of course, the active virus nose swab thingy might also have said positive when somebody didn't have it, right? That could have a false positive rate, in which case your estimate of this quantity would be off. But it's an easier thing to get a handle on than this side of the equation. I'm not sure if the pointer's showing up here or not, but then the left hand side of the equation, where it's the probability of corona given the positive antibody test. Okay, so it's easier to estimate this side. Well, we still have to talk about the denominator, but the basic idea is that it's easier to estimate this side, where you're estimating what's the likelihood of having had the virus outright, and what's the likelihood that if you have the virus, then you have a positive test, than it is to estimate what's the probability that you have it when assuming that you've got the positive test. So flipping it that way. Okay, for the denominator, what we can do is do something kind of similar, which is to say that the probability of positive test outright, we can use what's called totality of, well, just use conditioning and say, that's not really totality of expectation yet, it's just conditioning. We can say the probability of a positive test is the probability of a positive test given corona times the probability of corona plus the probability of a positive test given not times the probability of not. Okay, So we can just divide up the idea being that probability of corona and probability of not having corona. So these should sum to one. So this is like dividing the possible outcomes into two camps. And so we can take the conditional probability weighted by the two options and add those up, and then we'll get the total probability of a positive test. The idea being that either you had it or you didn't, and if we know the probability of each of those, we can multiply the probability of a positive test given corona by the probability of corona, probability of positive test given not by not, and get that. Okay, and so this is, the same term that was in the numerator here. So we're saying we're going to divide this by itself plus, so sorry, I should say it out loud in case the pointer's not showing up. The probability of corona times the probability of positive test given had corona is the same as the first summand of the probability of positive test down here. And so what we're doing is we're dividing this quantity by itself plus this thing, which is the probability of a positive test given not. And so how do we come up with this? Well, the probability of a positive test where you don't actually have the virus is what's called the false positive rate, because it's the probability of the test saying yes, but that's actually wrong. And then the probability of not having it is just, the one minus the probability of having it. And so if we've done our community survey to say that 5% of people had it, then the probability of not is 95%. If it's 20%, then probability of not is 80%. Okay. And so how do we come up with the false positive rate? Well, that's another thing you would measure about the um, test, right? So about like the, antibody test, you would want to know what its false positive rate is. And so um, you'd want to know what its false positive rate is. And so that one's a little bit harder to imagine how you would do, but I guess the idea is that, well, you want to sample only people who didn't have coronavirus. So you find people who you're pretty sure didn't have it. I don't know, maybe by like going to an area where there's very little community spread already, and then doing some nasal swabs on people that would detect an active infection, and then isolating them for 14 days or something, and then doing the antibody test or whatever. I don't know how long you have to wait for the antibody test to pick things up, but the idea is you could find people who you're pretty sure don't have it by doing some other test that, again, would have some errors, but you could do the test and wait and see if they develop symptoms and be hopefully pretty sure that people didn't have it. And then once you've got a population of people who didn't have it, you would give them the antibody test, and then you would see how often does it say yes. And if it says yes when you're already pretty sure they didn't have it, then that's a false positive. Okay, so okay, so that's the denominator there. Okay, so what does all this mean? Well, if we put it together, then what we're saying is that the probability of corona given a positive test is equal to the probability of corona outright times the probability of a positive test given that you had it divided by the same thing. So probability of corona times the probability positive test given corona plus the probability of not having corona times the probability of a positive test given none. Okay, and so now let's plug in some specific numbers just to get a feel for it. So if you imagine that you have an antibody test where the true positive rate is 94%, and the false positive rate is 4%. So note that true positives and false positives don't together like add up to 100% necessarily, right? So like the fact that these get close is sort of an accident. So the true positive is like 94% chance that if you have coronavirus, then the test says yes. 4% is the chance that if you don't have coronavirus, then the test says yes, right? So the 96% is the true negative rate, which is it correctly saying no if you don't have it? Okay, and so then if we plug this in here, then we could, for example, assume that the base rate, right, is like 5% of people have had it already. Then what we get is a calculation where we've got 5% times 90, oops, 5% times 94% divided by 5% times 94% plus 4% times 96%. And then if you do the math on that, I'll do it online, you get something around 55%. Okay, so why is that? Well, 5% of 94% is, not that different than 4% of 96%. But what's important here is that this small number, the 5%, is the probability of corona, the base rate, right? So that's like if we do a community survey and find that around 5% of people have had it, and this 4% is the wait, something went wrong here. Sorry, that was supposed to be here. It's the other way. Okay, that was wrong. Okay, so it's 5% times 94% plus, let's write it this way, 95% times the 4%. Okay, so 5% of people had the virus, 94% chance that the test says yes if you had it. 5% times 94% again in the denominator, then 95% is the dual of the 5%, right? So this is the how likely are you to not have had it just without doing any test at all, right? Is a 95% chance if we've done a community survey and, figured out that not only 5% of people had it. And then 4% is the probability of a positive test given not having it, that is the false positive rate. Okay, so the point here is that if only 5% of people have had it, and your test has a false positive rate of 4%, then the and a true positive rate of 94%, which is around the 95%, around the 95%, almost balances that, then you get only around a half a chance that you had it if you get a positive test. And so why is that? Well, the idea is that if you get a positive test, it could have been one of two things, right? It could have been a true positive and it could have been a false positive. And so the question is, if you already think that it's pretty unlikely, right? There's only a 5% chance 1 in 20 people have had it, then a even though a true positive test is much more likely in this sense over here than a false positive, right? There's a 94% chance of a true positive and a 4% chance of a false positive. So many more people didn't have it that you're much more likely to have been coming from that camp, which means that overall your chances are much lower than the 94%, right? Because if you think about like doing a bunch of these tests, right? So like you're going to be getting a bunch of positives. The positives were either true positives or false positives. And if you're getting if so many people are likely to not have had it, then a lot of your positives are likely to have been false positives rather than true positives. And so a positive test doesn't mean like, yes, there's a 95.4% chance that I had it. It means there's like a 50% chance that I had it. And so that should, you know, go into your mental model of whether you are safe or not, even if you get a positive test. It doesn't mean that you get the true positive rate. You should be thinking about biasing that based on the likelihood that you're in the prior likelihood that you're in the true positive or false positive camp. Okay, so that's, an important thing to take into account there. Now, if, on the other hand, we do the same calculation, um, but with a true positive of 94%, a false positive of, again, 4%. But then, like, we assume the base rate of, infections is like 20%, then we get 20% times 94% divided by 20% times 94% plus only 80% times the false negative rate of 4%, which then, if you work it out, is around 85%. So once your population level base rate of idea about how likely you are to have had the virus goes up a little, then instead of 50%, 55% on the last calculation, that goes up to 85% now chance that you had it if you have a positive test. And so by increasing the true positive rate of the test, decreasing the false positive rate of the test, increasing the amount of the population you believe has had it, right? So if you're in New York City and 20% of people have had it rather than 5%, then you get more certainty that a positive test really came from the true positive camp rather than the false positive camp. And it looks like, at least one of the antibody tests that people were talking about, they were claiming that the true positive rate was 100% and the false positive rate was 99.5%. And so then you can plug in your, community's base rate and do the calculation and see what you would think out of that. But it should be a pretty high number because you'll get, very few false positives. So maybe even on the 5%, that would be good there. But it's important in general to be taking into account things like this. That is, if you've got a relatively low chance that you had it without doing the test, then when you do the test, it's relatively likely to have come from a false negative rather than a false positive. And so you don't want to just be going on the true positive rate and assuming you're in that camp. You want to be thinking about the false positives as well. Okay, so in the next one, we'll look at what this has to do with spam filtering.